The USS Gerald R. Ford, renowned as the world's most advanced aircraft carrier, might also be the Navy's most expensive failure, with billions of dollars spent on unproven technology that may leave it vulnerable in real-world combat. This vessel reliability is now being questioned. Can the USS Gerald R. Ford overcome its technical challenges to fulfill its promise as the world's most advanced carrier? And given the rise of sophisticated missile technology from rival powers, can it truly defend itself against next-generation threats? Join us as we delve into the U.S.'s testing of all-new gigantic $13 billion aircraft carrier. The U.S. Gerald R. Ford Series CVN-78 aircraft carrier is the first of its kind in the Ford class. It is equipped with innovative technologies meant to enhance the performance, capability, and durability of the ship. Leading the way as the first of her kind, the Ford class presents innovations that are revolutionary when compared to the Nimitz class, and thus is the first in a new generation of aircraft carriers. The majority of the significant changes in the Ford class of carriers are represented by the Electromagnetic Aircraft Launch System, also known as EMALS. While some catapult systems still use steam to launch the aircraft, the EMALS uses electromagnetic fields instead, which is much more efficient and takes a minimal toll from the aircraft. This design system implies some future advantages of launches that are quicker and smoother to execute, which can contribute to a higher readiness level. Another is the Advanced Arresting Gear, also known as AAG, since it is intended for the accomplishment of the recovery of the incoming aircraft using energy absorption technology. This characteristic makes the Ford capable of accommodating more aircraft weights and flexibility in terms of missions. The AAG is developed to reduce mechanical stress when touching down, to enhance the quality and safety of a landing, while putting less pressure on the aircraft. By emphasizing the flexibility and durability of the equipment, the AAG contributes to the enhancement of the flexibility of the carrier that enables it to accommodate various types of aircraft with a higher level of accuracy. The Ford contains the generation known as dual-band radar, also known as DBR, where one radar does the functions for all the other different types of radar, making it easier to detect and track threats such as missiles and aircraft. This integrated radar setup is supposed to enhance the limitations of multiple threat scenarios and response accuracy for the carrier. Realizations that include the advanced weapons elevators are part of this efficiency in which munitions are moved to the flight deck at faster rates, hence increasing the readiness and responsiveness of the carrier during high-demand situations. The technological advancements jointly imply improving the effectiveness of operational utilization of the Ford-class carriers with proper organization of manpower and resources. With this new craft comes some major concerns. So what new concerns have arisen with the application of these new technologies to the Ford carriers? And how can the need for carriers be met and the challenges mitigated? The Navy's trials with EMALS and AAG on the USS Gerald R. Ford provide some valuable lessons in reliability engineering, showing that these challenging conditions, far from being exceptional, are in fact typical for contemporary naval operations. EMALS and AAG are new-age technologies aimed at accomplishing the job of customary steam-propelled catapult and hydraulic arresting gear in aircraft carriers. Whereas EMALS provides steamless electromagnetic forces to catapult planes into the air, AAG employs ultra-high energy absorption to arrest incoming aircraft for a smooth touchdown. Combined, they provide for enhanced takeoff and landing profiles with better turnaround times, which provides flexibility within Fenton's fleet to accommodate a broad range of airplanes. Nonetheless, experiments have revealed that some of these systems perform suboptimally to their operational requirements. However, in this respect, the System Enhanced Integrated Lifting System has been referred to as EMALS and revived with the Allied System of Annex as AAG, which is not always able to address the Navy's concern of achieving a high number of launches and recoveries with no faults or failures. For instance, in the case of EMALS, there have been problems with power load distribution and its general reliability, which sometimes result in shutdowns. While such faults may present themselves during other spacecraft launch phases, they can be especially damaging during launches due to their potential to disrupt a flight's timeline, diminish a mission's efficiency, or endanger aircraft and crew on board. It is worthy to note that at the time of carrying out these functions, the AAG has as well encountered its own reliability issues. Approved to accommodate a larger variety of payloads, From the lightweight UAVs to heavy fighter jets, AAG every now and then fails in operation tests, especially if used constantly. These problems add stress to maintaining aircraft and decrease the time actually available for flight utilization, thus lowering the sorties, missions per day/shift, that a ship can launch and recover. Due to these reliability issues with EMALS and AAG, the Navy has been forced to undertake reliability reviews and reliability improvements. Skill film technical deficiencies. Engineers and technicians are in the process of developing ways on how to improve the functional capabilities of these systems so as to achieve the extended operational need in terms of strength and reliability. A key purpose is to make certain that at any given time, EMALS and AAG are capable of providing support to the carrier's high operational tempo without closing up or coming to a standstill for repairs. Originally unveiled in 2017, the ship's defense systems, and most importantly, the radar and missile interceptors that are part of the air defense system of the USS Gerald R. Ford, are instrumental in covering the carrier and its complement, in addition to vessels in its company, against various threats ranging from missiles, drones, and aircraft. There are these systems that are specifically designed to not only identify threats and threats coming in, but to arrest and defeat them. But in general, the defense of the Ford has been questioned simply due to a variety of tests that showed some weaknesses on their part. The DBR, or dual band radar, is also part of the defense system to track numerous types of threats at once. Implemented as a single system, the DBR combines a number of radar functions, which theoretically at least provides the carrier with improved surveillance, response time, and efficacy. In the tests, the DBR has been demonstrated to be effective at tracking threats and giving the Navy important information about the speed, direction, and type of impending perils. Nevertheless, some drawbacks in simulations where several threats are present simultaneously, or where the threats may differ in kind, have been reported, such as differing between missiles and low-flying UAVs. This has given rise to the worry of whether radar is capable of managing complex events that would probably require the different dangers targeting the carrier to be addressed at the same time. In most cases, the targeting sensors that are utilized in the targeting process deliver good results in detection and tracking of target objects. However, there are some circumstances during the testing when interceptors cannot effectively fire or destroy the simulated targets. These failures indicate possible weaknesses in an approach to the carrier's multifaceted shield that should involve a number of layers designed to identify, track, and eradicate threats. Those concerns are being met by the Navy performing its due diligence, evaluating where and if improvements need to be made in order to get the most out of the Ford class's already strong defenses. Current efforts are being made by engineers to advance the radar's tracking signalization and concern the DBR with other anti-missile weaponry parts in order to respond to compound threats under intense conditions. The Navy's aim is to prove that every weapon system of the Ford is fully capable of achieving this firing solution against a variety of realistic threat scenarios that may be encountered by a flat top when it is committed to active operations. Therefore, how does this new Ford-class carrier's power and energy system differ from Nimitz-class or other older aircraft carriers? And what are the implications of these differences for current operations and efficiency or future capability? The Ford-class aircraft carriers are equipped with an advanced nuclear reactor system that produces approximately 3 times the power of the previous Nimitz-class carriers. This immense energy capacity is one of the defining features of the Ford class, enabling the ship to support a broader range of high-demand technologies and advanced weapon systems. The increased power output, around 125 megawatts, is critical for meeting not only the carrier's current operational needs, but also for accommodating future advancements in naval technology. One of the most exciting implications of this enhanced energy capacity is its potential to support next-generation defense systems, such as laser-based weaponry. Unlike conventional weapons, which rely on ammunition, laser weapons consume only energy, making them a sustainable and cost-effective option for intercepting threats like missiles and drones. The Ford-class carrier's surplus energy could power these systems continuously without overburdening its reactors, giving the ship the capability to defend itself against multiple high-speed or high-volume threats. This could be especially advantageous as the nature of naval threats becomes more advanced and varied, with potential adversaries deploying faster, smaller, and more numerous missile systems. In addition to laser-based defenses, the Ford-class carriers are well-positioned to integrate other energy-intensive systems that may emerge in the future. Electromagnetic railguns, for instance, require substantial power to launch projectiles at speeds far exceeding those of traditional explosives. Railguns would provide the carrier with a long-range, high-velocity strike capability that could target both air and surface threats with unparalleled precision. The increased power capacity of the Ford class means that it could support such systems without compromising other essential operations, allowing the carrier to maintain its role as a powerful offensive and defensive asset. These systems provide comprehensive situational awareness, a critical advantage in modern naval warfare, where fast response and adaptability are essential. The energy surplus also opens up possibilities for supporting emerging technologies like artificial intelligence and autonomous drones, which demand substantial processing power and energy. To sum it up, the Ford class's energy capacity serves as a future-proofing measure, allowing it to incorporate new technologies over its lifespan of 50 years or more. This adaptability ensures that Ford-class carriers can evolve in response to rapidly advancing military technologies and shifting defense strategies, making them a resilient platform for modern and future warfare. How do U.S. allies and partners perceive the deployment of the USS Gerald R. Ford, and what does that say about greater ramifications for international military cooperation and strategic partnerships? Recent deployments of the USS Gerald R. Ford to Europe have been more of strategic missions than purely an operational exercise, showing how serious the U.S. is concerning its defense commitments in partnership with NATO allies when geopolitics are heating up. The U.S. places the Ford in European waters. The Navy stresses the principle of collective security and pledges the allied nations continued assistance against regional threats, particularly in those cases when the adversarial presence or action may be challenging the stability. While in Europe, the Ford has performed numerous joint training exercises with NATO forces, this being an opportunity for the carrier and her crew to work directly with other allied naval units. This kind of collaboration represents really useful training for all the participating forces to perfect the joint operational tactics, share strategic intelligence, and foster interoperability between myriad military branches and technologies. Working with NATO allies in exercises such as air defense drills, anti-submarine operations, and maritime security simulations, the Ford helps to standardize procedures among those nations so they'll be able to operate together if a real-world conflict ever comes up. The presence of the Ford also represents strength and unity within the NATO alliance. To be in a position to host one of the most advanced aircraft carriers with allied fleets is a very strong message that NATO still remains formidable in protection and defense of its membership and values shared among its membership. This will enhance deterrence by underscoring the collective defense capability that would respond to hostile action. It is also a visible reminder of the capabilities and cohesion of NATO, a factor of dissuasion of hostile acts, because it shows that the alliance is ready and willing to react together against any threat. Besides reinforcing military cooperation, such deployments are an opportunity for the Ford and its crew to gain experience in operations under various environmental conditions, as well as with other NATO forces. Cross-training with NATO forces provided valuable exposure to the protocols and procedures of allies, furthering a deeper level of mutual understanding and respect between the forces, a necessity toward effective joint operations. That integration of advanced Ford capabilities with those of NATO allies ensures that the deployment further enhances the readiness of the alliance against both conventional and non-conventional threats, now and into the future. Given that each Ford-class carrier costs around $13 billion, how do the projected operational savings and efficiencies translate into overall cost-effectiveness throughout the carrier's expected service life? The USS Gerald R. Ford's construction, costing approximately $13 billion, marks it as the most expensive warship ever built. This significant investment reflects Ford's advanced capabilities and the extensive research and development efforts required to incorporate next-generation technologies. Although the price tag has been met with scrutiny, the Navy believes that the long-term operational savings will justify the initial expense by reducing overall lifecycle costs, making the carrier cost-effective over its expected 50-year service life. One of Ford's major cost-saving features is its smaller crew size. The Ford-class carriers are designed to operate with around 20% fewer personnel than the Nimitz-class carriers, reducing the crew from about 5,000 to approximately 4,000, including air wing personnel. This reduction is possible due to the automation and efficiency improvements embedded in the ship's systems. Automated weapons elevators, advanced digital controls, and more efficient shipboard processes help streamline tasks that traditionally required more manual labor. Fewer crew members mean lower personnel costs, such as wages, benefits, and training, which are substantial portions of the overall operational budget. Over time, this lighter crew requirement is expected to generate significant savings. Another major area of projected savings lies in the extended periods between maintenance overhauls. The Ford-class carriers are built with more durable and efficient systems designed for extended operational availability. For instance, the Ford's nuclear reactors have an extended life cycle, allowing the ship to operate continuously for longer periods before needing major refueling and maintenance. This enables the Ford to spend more time deployed or in active service and reduces the frequency and cost of lengthy, costly maintenance periods that traditionally took Nimitz-class carriers offline. This increase in operational availability maximizes Ford's service time while minimizing downtime costs. Ford's fuel efficiency further contributes to its cost effectiveness. Although nuclear-powered carriers do not require traditional fuel, they still rely on large amounts of fuel for their aircraft and other onboard systems. Beyond these cost-saving features, the Ford's design also anticipates future upgrades and modernization efforts, allowing new technologies to be integrated more easily and cost-effectively. The ship's modular construction and increased energy capacity are intended to simplify the addition of future systems, such as laser weaponry or advanced radar, without requiring extensive retrofitting. This flexibility lowers the financial burden of keeping the ship technologically current, extending its relevance over the decades, and potentially avoiding the need for entirely new carriers sooner than expected. In what ways does the training of crews for the USS Gerald R. Ford differ from that of previous aircraft carriers? And how do these changes reflect the integration of advanced technologies and operational requirements unique to the Ford class? Training programs for the crews of the Ford-class aircraft carriers have undergone significant updates to align with the advanced technologies integrated into these modern vessels. As the USS Gerald R. Ford incorporates systems like the Electromagnetic Aircraft Launch System, EMALS, the Advanced Arresting Gear, AAG, and various integrated combat systems, the need for specialized training has become paramount. These systems represent a shift from traditional naval operations, necessitating a comprehensive approach to ensure that crews are fully equipped to operate and maintain these cutting-edge technologies effectively. The training curriculum now places a strong emphasis on the operational aspects of EMALS and AAG. EMALS, for instance, replaces the conventional steam catapults used in older carriers, requiring crews to adapt to new procedures for launching aircraft. Training programs include hands-on simulations that allow personnel to practice launching a variety of aircraft under different conditions, familiarizing them with the system's controls and emergency protocols. This immersive approach helps build confidence in using EMALS, ensuring that crews can execute launches efficiently and safely during real-world operations. Similarly, the Advanced Arresting Gear requires specific training to handle the complexities of recovering aircraft. The AAG system utilizes energy-absorbing technologies that differ significantly from previous hydraulic systems. Crews must understand the mechanics of the AAG, including its various components, and how to troubleshoot potential issues during recovery operations. Training exercises include simulated landing scenarios that replicate the dynamic conditions of actual flight operations, allowing personnel to experience the nuances of the AAG in a controlled environment. Furthermore, the training programs have been designed to incorporate integrated combat systems that enhance the carrier's defensive and offensive capabilities. These systems include advanced radar, missile defense, and communication technologies that allow for real-time data sharing and situational awareness. In addition to hands-on training, the Ford-class training programs leverage virtual reality, VR, and computer-based simulations to create realistic operational environments. These technologies provide crews with opportunities to experience various scenarios without the risks associated with live exercises. By using VR, personnel can engage in emergency drills, practice routine operations, and gain familiarity with the ship's layout and systems before stepping aboard the actual vessel. This innovative approach enhances retention and comprehension, ensuring that crews are better prepared for their responsibilities. The emphasis on updated training programs reflects a broader commitment to ensuring that the Ford-class carriers can operate at peak efficiency from day one. By investing in comprehensive training tailored to the unique technologies of the Ford, the Navy aims to maximize operational readiness and minimize the potential for errors during critical missions. As the Ford-class carriers enter service, the effectiveness of these training initiatives will be vital in determining how well the crews can leverage the ship's advanced capabilities to meet modern naval challenges. Ultimately, this thorough preparation will contribute to the overall mission success of the Ford-class carriers as they engage in strategic deterrence, power projection, and allied operations in a rapidly evolving global security landscape. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.